Okay, good afternoon, pilot teachers, and good afternoon, students.
Good afternoon, Mr.
Thank you, sit down. Okay, we have actually started on the next booklet, and that is to do with the introduction of climate. And from our last lesson, we generally looked at some of the important lines of latitude, and the reason for why it is important for us to look at those lines is because they have to do with the distribution of climate. To recap very quickly now on what we are going to do for the lesson, we're going to do two objectives, and they are, one, to describe the movement of the Earth, and two, to explain the effect of those movement of the Earth. And when we are looking at our lesson today, we are going to look at basically the first movement, and that is the movement of the Earth's rotation. We'll look at the movement of the Earth's revolution in our next lesson. So basically our lesson today, those would be the two objectives I'd like us to be able to achieve. But before we go ahead to looking at those two objectives, let's recap on the important lines of latitude that we had time to go through yesterday. We start off with the most center line, which divides the Earth into equal half, keeping in mind that the lines of latitudes are lines on a map which runs from west to east or east to west. The longest line of latitude that divides the Earth into equal halves would be the equator. Then 23.5 degrees to the north sits the line Tropic of Cancer. 23.5 to the south is the line Tropic of Capricorn. Any region that falls within the Tropic of Cancer and the Tropic of Capricorn are said to have tropical climates. Okay, we move further north from the Tropic of Cancer. We come to the 66.5 degrees to the north, which is the Arctic Circle. And in the south, from the Tropic of Capricorn to 66.5 to the south sits the line, the Antarctic Circle. Any area that is found within 23.5 to the north to 66.5 north and 23.5 south to 66.5 south are said to have temperate climates. And then finally, we have the area which is the furthest north, and that is the North Pole that sits at 90 degrees, and the area further south, which is the South Pole, sitting at 90 degrees. Any region that falls between 66.5 north to 90 degrees north and 66.5 south to 90 degrees south are said to have polar climates. Those lines of latitude are important lines. Again, be reminded that they are imaginary lines. You do not fly in aeroplanes over and then you will see the equator, no. But you will be told that you are crossing the equator, as well as the Tropic of Cancer or the Tropic of Capricorn, depending on where you are flying. But also note, those lines are lines which run from west to east, or horizontal, across from one side of the map to the other side of the map. Okay, we move on. Today, what I'd like us to look at now would be the movement of rotation as well as the movement of revolution. The Earth has, or it does, two very important movements, and those two movements also contribute to affecting the climate of the Earth. Okay, looking at some of the basic facts that we have already covered in our last lesson, we looked at the Earth is actually shaped like a sphere or a globe. The Earth is tilted at an angle of 66.5 degrees. The Earth does two movements, and the first one is rotation. The Earth rotates on its axis every 24 hours, and the Earth rotates from east. Sorry, I'll rephrase that. The Earth rotates from west to east. So the first movement, as demonstrated by the globe here, is the movement of rotation. And the Earth does this 24 hours. And it rotates from west to east. That's the first movement. With this movement then comes the effects. While the Earth is actually rotating, the effect that it has would be resulting in day and night. So all of those areas which are actually facing the sun would be experiencing day. All of those areas which are away from the sun will experience night. And it takes about 12 hours of daylight, especially for areas within the equator, and 12 hours of night. So if we had the sun on my right hand, that means that all of these areas here which are facing the sun on this globe would be experiencing day. Meanwhile, on the other side, on the left, all these areas here will be experiencing night. And that is one of the important effects of the movement of rotation. The second important effect on the movement of rotation is the difference in heating of the Earth's surface. The areas which are facing the sun, note, during the day, they would be a little bit more warmer than those areas which are away from the sun, or those areas which are experiencing night. And that's basically what we mean when we talk about the difference in heating of the Earth's surface as a result of the Earth's rotation. I'd like us now to look at the information from the handout which I had distributed, and we'll go ahead with more explanation on the movement rotation as well as the effects of that particular movement on rotation. So if you can make reference now to that handout or the worksheet, of which it titles Our Earth's Two Important Motion. Okay, we read, or I'll go through and you follow. The Earth has two very important motions or movements which influence all of us. The Earth rotates or turns around or spins on its axis, and it revolves or circles or orbits around the sun. The Earth's rotation results in our experiencing night and day in every 24 hours. At any one time, half of the Earth is facing towards the sun and experiencing daylight, while half the Earth lies in its own shadow, facing away from the sun and experiencing night. As the Earth turns on its axis, daylight and darkness continue to sweep around the world every 24 hours. The fact that we see the sun rise in the east, move across the sky, and set in the west shows that we are turning with the Earth from west to east. By imagining ourselves looking down on the Earth from above the North Pole. Okay, we'll have to imagine now that we are looking down on the Earth from the North Pole. So if we can make reference to this diagram here. So if we are standing above and we are looking down the Earth from the North Pole, this is what we would be seeing, this diagram here. Similarly, if you were standing, making reference to the globe, if we are standing at the top there, maybe where the light is, and we are looking down to the North Pole. Okay, that information we'll read on and find out why it's important for us to note that. By imagining ourselves looking down on the Earth from above the North Pole, the direction of the Earth's rotation would be seen as anti-clockwise. Okay, here you can see the arrow, these two arrows here. They are showing the rotation of the Earth. And if we stood above and looked down, then we would have seen the anti-clockwise rotation of the Earth. And that's what the diagram is explaining. Strangely enough, all movements in the solar system, which includes the orbits of the planets around the sun, the rotations of the planets on their axis, and the movement of the moons around their planets, are all the same, and they all rotate in an anti-clockwise direction. In doing so, we note that the Earth, while rotating on its axis, seems to be doing the rotation just at the right speed. And that speed is 24 hours for it to complete one full rotation. You're following? Okay, we are now going to look at the information from the chart here, of which it gives us an idea also about the rotation of the other planets in comparison to the Earth on their axis, and how many hours or perhaps how many days it would take for the other planets or for those other planets to complete one full rotation. Keeping in mind, the rotation is the movement whereby the Earth spins on its axis from west to east, and it takes 24 hours for the Earth to complete one full rotation. Let's check with the other planets and find out also the time it takes for the completion of one rotation. While we are looking at that information, perhaps the other information that I have also put up on the chart we might want to look at, as it might help us maybe understand a little bit more about the movement of rotation and also the movement revolution. So here we have the 9 planets of our solar system in this particular column. The second column here generally gives us information about the diameter of each of those planets in kilometers. The third column tells us the number of moons that each of those 9 planets have. The fourth column gives us information about the average distance from the sun in millions of kilometers. The next column shows us the time it takes for each of those planets to orbit the sun. And finally, the time taken to make one rotation on each of those planets' axis. And for the Earth, we say it will take 1 day, which is 24 hours for a complete rotation. Okay, we check. Let's look at the last column only, just to make a comparison of the hours or days it takes for the other planets to complete one rotation, one full rotation. We know already the Earth, it takes 1 day, which is 24 hours. We go to Mercury. Mercury, it will take 59 days for it to complete one full rotation. Is that fast or slow? It's very slow, yes. If it takes 1 day for the Earth to make one rotation, Mercury, it takes 59 days for it to complete one rotation. Venus, it takes 243 days to complete one full rotation. The Earth, we know already 1 day, which is 24 hours. Mars, it will take 1 day, similar to the Earth, 24 hours. Jupiter, it will take 10 hours to complete one full rotation. Is that fast or slow in comparison to the Earth? It's fast, very fast actually, maybe 5 hours of night, 5 hours of day. Saturn, 10 hours, similar to that of Jupiter. Uranus, it will take 11 hours for a complete rotation. Neptune, it will take 16 hours for a complete rotation. And finally, Pluto, it will take 7 days for a complete rotation. Okay, so we're making a comparison of that movement, which is rotating on its axis or spinning on its axis. And for the Earth, we say it will take 24 hours, which is 1 day, for the Earth to complete one whole rotation. Okay, so while we are still on this information here, we might also look at the other information that I have put here, maybe for us to be able to make a comparison with our planet Earth. Diameter in kilometers for the 9 planets. Mercury, 4,880 kilometers. Venus, 12,104 kilometers, the diameter of Venus. Earth, 12,756 kilometers. That's the diameter of the Earth. Mars, 6,787 kilometers, the diameter. Jupiter, 142,800 kilometers. Saturn, 120,000 kilometers. Uranus, 51,800 kilometers. Neptune, 49,500 kilometers. And Pluto, 3,000 kilometers in its diameter. Number of moons that these different planets have: Mercury, none. Venus, none. The Earth has only one moon. Mars, 2 moons. Jupiter has 14 moons. Saturn has 10 moons. Uranus has 5. Neptune with 2 moons, and Pluto 1. The distance from the sun for each of those planets. You would have noted that the closest planet to the sun is Mercury. Therefore, as we go from Mercury to Pluto, the distance will definitely increase. 58 million kilometers from the sun is the planet Mercury. Venus is 108 million kilometers from the sun. The Earth that we are interested in is 150 kilometers. I'll repeat that, 150 million kilometers from the sun, and etc. until we come to Pluto, which is the furthest. So the Earth, we are at 150 millions of kilometers from the sun. Okay, we move on. The time taken to orbit the sun. This is the next movement that we are going to move on to, and that is the movement of revolution. We already note about the rotation, but let's look at the amount of time it takes for each of those planets to actually orbit the sun. Mercury, it will take 88 days to complete one full revolution. Venus, it will take 225 days to complete one full revolution. The Earth, it takes 1 year, which is 365.25 days. Mars, it will take 2 years for it to complete one full revolution. Jupiter, it will take 12 years to complete one full revolution. Saturn, it will take 29 years to complete one full revolution. Uranus, it will take 84 years to complete one full revolution. Neptune, it will take 165 years to complete one full revolution. And finally, Pluto, it will take 248 years to complete one full revolution. Okay, having some of this information for us to actually work with, these are basic facts. I think this you've already covered in science in grade 9 and 10 or grade 7 and 8. We move on. Some questions for you to actually think about. Can you imagine what it would be like if our daylight period lasted about 4 months? So instead of having 12 hours of day, imagine if the daylight period lasted 4 months and was followed by cold night that lasted another 4 months. That is like on the planet Venus. If our planet was like Jupiter, daylight would last only 5 hours, and it would be followed by 5 hours of night. Do you think this would be better? Well, again, you might have your own opinions, and then you might have to discuss and decide on whether you think it would be better or not. But these are some questions perhaps for you to think about, and you'll find those questions on the handout at the end of the work on the Earth's rotation. So looking at that information again, what we have covered so far, we have looked at the movement of the Earth in terms of the Earth rotating it is important for us to note that the Earth rotates on its axis every 24 hours from the direction west to east. While the Earth is actually doing that movement of rotation, two very important effects are noted. One, that is day and night. And number two, we have the difference in heating of the Earth's surface. Note about the difference in heating of the Earth's surface. I explained that those areas which are directly facing the sun would experience daytime, and those areas which are away from the sun that are not facing the sun are actually in night. This diagram here would show the sun shining on this part of the Earth, resulting in this area here experiencing daylight. And away from the sun, we have the shadow, showing us then the areas of the Earth experiencing night. But that comes about as a result of the Earth's rotation. If we were standing above the North Pole looking down, we would have noted also that on the Earth's rotation, the rotation will always be in an anti-clockwise direction. And likewise, all the other planets also, they rotate in an anti-clockwise direction on their axis. Any questions so far? You have a question? No question? Gibbs, there's a question. Okay, Gibbs, your question.
Why is it that the days in Mercury, the Earth has to turn 1 year revolution, and the Mercury has 88 days for one revolution? Why is it
88
days for one revolution around the sun?
It is actually closer to the sun. It goes a little bit faster in terms of its orbit around. If we're looking at the orbiting of the planets around the sun, okay, let's assume that we have the sun here, okay, the sun, and then the closest planet to the sun will be Mercury. So for it to complete that orbit, it has a smaller space of which it will move around in comparison to the other planets as we move away from the sun, of which if we have Mercury here, then the next planet will be Venus to orbit around. It would have a larger distance to actually go around. Then we have Earth, which has a larger one compared to the other planets which are closer to the sun. Therefore, the days it takes for the planets to orbit those closer to the sun, it is a little bit more faster than those that are further away from the sun. You see, Pluto is the furthest planet from the sun. Therefore, because of its distance, it will take a longer time to complete the revolution right around. Does that answer your question? Francis has a question.
Why is it that the planets around the sun cannot float away in space?
Why is it that the planets around the sun cannot float away into space? In the beginning, when we looked at the formation of the Earth, we also noted that the gravitational pull of the sun also contributed to the pulling of all the other planets in towards a center mass, which is the sun. So the gravitational pull of the sun and also all the other planets with their gravitational effect contributes to them coming towards a center point, and the center point is the sun, and that's where we have all the planets actually staying together within that orbit or within that motion right around. So it's to do with the gravitational pull in the beginning when the Earth was first formed, similarly to all the other planets when they were first formed. From our study on how the Earth was formed, we looked at the heavier and the heavier materials settled towards the center of the Earth. Similarly to all the other planets, the heavier materials settle to the center of those planets. And those materials also have a gravitational effect, of which the gravitational pull of the sun also will contribute to them pointing, not only pointing, but staying within that motion and the orbit in space. Does that answer your question? Okay. Val has another question.
My question's on Venus, the rotation of its own axis. How come it takes longer time than Earth, where it takes 1 day, and Earth is larger than Venus?
You're looking at Venus?
Yes, the rotation on its own axis.
Okay, for the rotation part, unlike for the revolution, we can say that the planets closer to the sun will take shorter time for them to go around in comparison to those that are further away. But for the spinning or the rotation of the planets, it is not those closer to the sun that will spin fastest, no. It depends on how fast each of those planets is actually supposed to or is rotating around. And that's the reason for why it is in comparison to the Earth, it will take 243 days for it to rotate. It's rotating at a very, very slow pace right around. So the spinning or the rotation movement of each planet does not have anything to do with whether they are close to the sun or not. But the revolution, definitely. If you are closer to the sun, not you, but the planets are closer to the sun, the shorter is the revolution for them in comparison to those that are further away, where it takes a long time for them to complete one full revolution. Last question, and then we'll move on.
For the difference in the diameter, compared to Jupiter compared to the Earth's diameter, the Earth's diameter is less than the Jupiter's diameter. And is there why is that the Jupiter in the rotation on its own axis has 10 hours then? Having 24 hours.
We're looking at this again?
Yeah.
Okay, again, we're looking at, depending on the Earth while it's spinning around on its axis, we're looking at 10 hours for Jupiter, and we're looking at 1 day for the Earth, and yet you are saying that for the Earth, the diameter is actually smaller, and it takes 24 hours, and for Jupiter, it has a bigger diameter, and it takes 10 hours. That's your question. Why is it that the Earth spins faster, even though it has a larger diameter? Okay. Is that the question you're asking?
Why is that Jupiter turns more faster than the Earth?
Even though it has a
Larger
diameter in comparison to the one for the Earth. Okay, good question. I will have to actually research on this one so that I'll give you the correct answer. I will go off and find the answer to that question, and I will come back in our next lesson. We'll see if we can discuss the reason for why that is so. Okay, keep that question in mind. He's going to repeat the question again, and for anyone who's watching can also see if we can find an answer for our next lesson for that particular question. Would you like to repeat your question, and we'll research on it together? We'll come back with an answer in our next lesson.
The diameter of Jupiter compared to the diameter of the Earth is greater than the diameter compared to the Earth. What, is there a factor contributing to the rotation of the Jupiter and Earth?
Okay.
Rotation on its own axis.
Okay, we're looking for a reason. We're looking for a reason for why is it that even though Jupiter has a larger diameter compared to the Earth, the rotation is much more faster than that of the Earth. And we're going to research on that one, and we'll come back with the answer to that question, as I do not have the answer, and I might not be giving you the correct answer now. Until I find the correct answer, we'll look at it together in class. Okay, we'll keep that question in mind. We'll move on. Okay, for us to move on then, we are going to look at the next movement. And for the next movement that we are going to move on to, I'm not going to explain into detail because I'd like us to cover that in our next lesson. But generally, the second movement that the Earth does beside rotation is the movement of revolution. And the Earth revolves every 365 and a quarter days around the sun. Okay, we have already made a comparison when we looked at the other planets also and how long it takes them for a complete revolution. To demonstrate and to show you this particular movement, the second movement of the revolution, we'll get Val to come and sit here, and she will act as our sun so that we can see the way in which the Earth is actually revolving around the sun. Okay, we must bear in mind the first movement we've done already, and that is the movement of rotation. The Earth always rotates, but at the same time, it will revolve around the sun. So here is the sun. Note, the Earth does not go around this way. Okay? It doesn't go in that manner, a circular motion. Rather, it goes in an orbital motion around the sun. So here goes. If this part of the Earth is actually facing the sun at one time of the year, when the Earth is actually in orbit, the Earth continues to rotate, but at the same time, it will go in an orbital motion, and the orbital motion is as shown or demonstrated here. Okay? The orbital motion is not right around, a circular motion right around, no. The Earth orbits in this motion around the sun. Okay, and while it is doing that, while it is actually revolving around the sun, note, if this part of the Earth here is actually facing the sun, certain seasons are experienced on the different parts of the Earth, because the revolution of the Earth has an effect on the Earth's seasons. Okay, I'd like you to keep your eye on the North Pole and the South Pole. The North Pole and the South Pole, when the Earth is in this position here. The equator is actually closest to the sun. When the Earth, it will take about 3 months for the Earth to reach this particular position in its orbit. Which hemisphere now is closest to the sun? The southern hemisphere, when after 3 months and the Earth reaches this point. Therefore, in the southern hemisphere, because the sun is closest in this area, the regions or the areas in the south experience winter. Meanwhile, those people in the north experience, we'll rephrase that. The people in the south, especially the fact that the southern hemisphere is closest to the sun now, those countries in the southern hemisphere will experience summer. Meanwhile, in the northern hemisphere, can you see the North Pole? On this globe, it's furthest away from the sun, therefore, winter is experienced. It will take 3 months for the Earth to reach this position. Now the equator is closest to the sun. What season is experienced then? Spring and autumn. Good. It will take another 3 months for the Earth to be in this position. Which area is closest to the sun? The north. This time, the northern hemisphere experiences summer, the southern hemisphere experiences winter. Another 3 months, and we are back to here, which is 365.25 days. Okay, so while the Earth is actually revolving around, it is also contributing to the seasons that are experienced. Thank you, Val. Okay, the effects of the revolution, the seasons, and we are going to go through the explanation of that in detail in our next lesson, and as well as that, the varying length of day and night. When seasons are experienced in the different parts of the world, we note that those areas which are facing the sun during one particular season will tend to have longer hours of daylight in comparison to those that are away from the sun. So the North Pole, if it is, or let's say the Northern Hemisphere, is in a position whereby the sun is closest to the areas in the north, then the countries in the northern hemisphere tend to have more hours of daylight compared to night. In the southern hemisphere, it's the same. If the sun is closest in the southern hemisphere, then the countries in the southern hemisphere experience more sunlight or hours of sunlight compared to night. And that is the reason why some countries also have what we call daylight savings, because they have extra hours of daylight, of which they can do a little bit more extra compared to the normal 12 hours of day and 12 hours of night. I think with that information, it will also bring us to the end of our lesson. We look at the explanation for the seasons and varying length of day and night in our next lesson. But for your homework, what I would like you to do is, in your exercise book, I would like you to construct a diagram, and that diagram should help you explain two things. One, the day and night in terms of the effect of the Earth's rotation. That's number one. And number two, the difference in the heating of the Earth as a result of the movement rotation. So we have looked at the movement rotation. For your homework, what I'd like you to do is I'd like you to explain, with the help of a well-labeled diagram, the effects on the Earth's rotation resulting in day and night. And number two, using the same diagram also, you can explain the reason for why there is a difference in the heating of the Earth's surface as a result of the rotation of the Earth. Okay, so those will be the two activities I'd like you to complete for your homework. Okay, class, if you can stand up now, that also brings us to the end of our lesson. To the pilot teachers, our keyword for lesson 85 is rotation. Good afternoon, and thank you, students.